Hello and welcome to my Open vSwitch conference talk. I'm Ben Pfaff. I work for VMware, and given that you're at this conference, you may have heard of me as one of the founders of the Open vSwitch and OVN projects. So this talk started out as being all about the ddlog incremental computation engine for OVN and the ways it worked well and the ways that it didn't. But as I thought about it more, as I stepped back a little, I realized that there's kind of a bigger story here. And so I want to give everybody the benefit of that, and I promise I'll get to the incremental bits in ddlog toward the end of the talk. So the basic problem in Open vSwitch and in OVN is when a packet shows up as part of our system, what do we do with it? And there's a lot more that these systems do, but personally, I see that as the most difficult question and the one worthy of the most serious study. So let me explain why I see a bit of a challenge here, a kind of a fundamental challenge. And I only realized this a little while ago, and I'd really love to hear people's comments on it because maybe there's something important that I'm missing, and if so, I would very much like to hear about that. So suppose we have a system where we have n VMs, or they could be containers or something else. So if we're going to configure those in our system, then we need order of n data to describe that. At least we need to know how each of them is configured and where it resides and what policies should be applied to it. So we probably pack those VMs several to a server or a hypervisor. I'll just call the hypervisors nodes. So since that's only a constant factor, we have big O of n nodes as well as VMs. Now, to get our system to operate correctly, each node needs to have the policy data, and it needs to be distributed to all those nodes. So we have O of n data and we have O of n nodes, so we multiply those together, and we have to use O of n squared bandwidth to distribute this. And this is true regardless of how we do that distribution. We might do it with OVSDB and OpenFlow or P4 runtime or BGP or whatever. And it just doesn't matter. The arithmetic is simple and true regardless, with one asterisk that I will that I will get to on my next slide. So the problem with this is that as n gets large, n squared gets even larger, and it's probably too much. And how do we arrive at some kind of a compromise? So here's my asterisk. If we can distribute the policy via multicast, then we only use O of n bandwidth to distribute O of n data to O of n nodes. I don't know an SDN system that takes advantage of that, and if you do, then I'd like some references. Maybe my overall argument here is defeated, so tell me. So now I'm going to go over some of the ways that we can compromise here, so that this n squared problem is less of a problem, and I'll get to incremental computation, incremental control at the end of this list. So be a little bit patient. So first, if n is small, then n squared is also relatively small, and if we look at early versions of OVN, as you can see from some of the talks at old OpenStack conferences, n equals 2000 was fine. And as it got up toward n equals 3000, it was not fine anymore. And if you look at a typical enterprise customer of my employer, for example, most of them have 7 or fewer racks. So n equals 2000, which is and my guess is that much larger n is fine today, would also be fine. And you might find that the definition of large is larger than you expect. The newest ovn-northd is remarkably fast and parallelizes quite well, and it might be a waste of time chasing users with much larger N. The startup I was at spent a long time chasing a large company whose name started with a Y and ended in an exclamation point. This was a waste because that customer was so large and so custom that that what we did there wasn't going to apply in any straightforward way to other people. So keeping n small is quite practical in a lot of cases. So another thing you can do is to try to reduce some of the constant factors while still remaining O of n squared. So here are some that have been implemented in practice. You can make sure that you're sending the same policy, same uniform policy to all the nodes. Instead of having your controller customize it to the foibles of the individual nodes, and OVN and NSX and other systems actually do that. You can send just the subset that actually applies to a particular node to that node, leaving out the other bits that don't matter to it, and OVN does that too. You can do compression either in terms of something like zlib or by representing the policy in a more compact form. OVN's address set and port group features do this, for example. Finally, you can keep your policy as simple as possible so that you don't have to say as much about it. Another potential way to solve things is sort of harks back to the origins of SDN and OpenFlow. So in the early days of OpenFlow, because it was easy, the controllers tended to work reactively. Which means that each time a connection showed up, the switch would send its headers to the controller, and the controller would tell the switch what to do for just that connection. This was easy to implement, but it caused latency because of all the round trips to the controller. It imposed a high load on the controller, and it didn't handle failures well. So the next generation of controllers were all proactive, meaning that they figured out what would need to happen to any conceivable packet and told the switch that in advance, and that sidestepped that problem. It caused this O of n squared problem we're talking about now, though. So you might think of things in terms of an analogy to Open vSwitch's internals, which once worked a lot like those reactive controllers. And to solve that problem in Open vSwitch, we invented something called megaflows, which you can read about in our NSTI 2015 paper. Can we come up with something like megaflows for controllers so that they're sort of reactive, but not as reactive, and the performance is better? Maybe. I don't know anybody who's tried exactly this. Another possibility is we could divide our network into smaller networks and then use a hierarchy or a federation of controllers. If our networks are mostly independent, so that this doesn't make things basically, so that this doesn't end up recapitulating the original n squared problem and just adds complexity, then this could be a win. We could assume that our network just doesn't change very much. If our network is static, so that we don't have to distribute n squared data very often, maybe it doesn't matter. Who knows? Another approach is SDN assumes a centralized controller. Do we actually need that centralization to achieve our goals? Usually the goal is not to be a shining example of the spirit of SDN. Usually the goal is to make our application work. Maybe we don't need to centralize everything, and maybe the nodes can do what we want with less communication. Maybe you need something simpler. So maybe we can get away with that in any given actual application. Finally, what about if we make our network very predictable? if, for example, we can set up our VMs so that each of the nodes can infer what needs to be done and where things live based on Ethernet addresses and IP addresses, instead of explicitly distributing policy data to everyone, maybe we can avoid distributing that at all in cases. That would be a lot like this might be a special case of the previous example where we say that we don't need to centralize it, that this is one way to not centralize. And then finally, let's talk about incremental control. And this is what this talk is really about. So so far we've been assuming that we need to send the full set of policy data to everyone basically all the time when things change. But if instead, when we have a small change to our VMs, we do a small amount of computation, and that changes a small number of logical flows, and then we just send that change to each of the nodes. And then on each of the nodes, we can efficiently compute from the logical flows that changed, the physical or open flow flows that need to change. Then we've got something that's much cheaper. Now, there are several assumptions that this builds on, and I haven't seen these assumptions actually laid out explicitly in the past. So let me do that now. So our first assumption that wasn't on our previous diagram is that our cold start has to be fast enough. And by cold start, I mean that you're starting out with a database of size n, and we need to distribute the initial state, and we need to be able to compute the initial state. So we're not escaping n squared entirely, but we're escaping it at runtime, just not at startup. So let's go through each of the other assumptions here. So first, we're assuming that the changes are small. If the changes are big, then there may not be any benefit. A big assumption we're making is that we can efficiently compute the changes to our logical flows based on the changes to the virtual machine policy. We're also assuming that when there is a small change to the policy, there's a small change to the logical flows. Now, I've bolded B and C because these are significant assumptions that we'll come back to in later slides. A simpler assumption that isn't very hard is that when you have a small change to logical flows, you can efficiently distribute it, and the nodes can efficiently receive that. Finally, a final big assumption is that if we have a small change to the logical flows, we can efficiently generate the differences to the physical or open flow flows. And finally, we're assuming that OVS, or whatever is running on our nodes, can actually handle those deltas efficiently. So let's break down the more difficult of these assumptions. So first, we're assuming that if there is a small change to the input, then the change to the logical flows is not much bigger than that. If we make a small change to the policy and everything changes in the output, then we're not going to do well. On the other hand, if it happens occasionally, then it might still be okay in practice. And we actually had a bit of a problem with this in OVN load balancers. So in some cases, changing one load balancer in a simple way, if that load balancer was important enough, then it could affect a hugely disproportionate number of the logical flows and thereby use up a lot of CPU time and bandwidth. In fact, this has been identified. This has been addressed through the addition of the concept of load balancer groups. I haven't studied those, but I'm sure that that's the solution. So the other big assumption is that given that we have a small change to input in in the network as a whole and on each individual node, that we can efficiently compute the changes that need to happen to the outputs in this case. And this is a harder problem. And the two places in the system where it has to happen are complicated code, and it's hard to rewrite them so that instead of looking at everything and generating everything in the output, they instead look at what changed in the input and they just generate the changes to the output. And in fact, we've tried three approaches over time. The earliest approach was implemented by Ryan Motes in 2016, and he wrote ad hoc code in C in the node controller that tried to detect when there were small changes to the input and just write those changes to the output. This was really hard to do correctly, and we weren't able to make it reliable at the time, and it got reverted. There's a more disciplined approach in C in the same code that seems to be much more successful. Han Zhao implemented this starting a couple of years ago. It uses an engine of C callbacks, and it still is working. I believe there are still some known issues based on the tests, which I think some of them are known to not be entirely reliable if in the incremental mode. I haven't looked at it recently, so maybe that's been fixed by now. And then finally, the project that I pursued with Leonid Rizik and Justin Pettit is automatic incremental computation with the ddlog language, and I'll talk about that more now. So ddlog is a language that you write code in the ddlog language, and it generates an incremental computation function for you automatically. So this is great in the best case, and we have a benchmark that I got from someone at Red Hat, which starts from an empty database and adds a router to OVN 250 times. And so the C version of this, it starts out really fast because the network is small, so that it runs in 0.14 seconds. But by step 250, that each individual step takes over a second. And so the total runtime for this is 107 seconds. Now the ddlog version, which where a ddlog does incremental computation automatically, it starts out at 0.13 seconds, and in step 250 it's only increased to 0.15 seconds. So the total runtime is basically just 0.13 times 250, and our total runtime is much faster. And you can find the details from that on the mailing list. Unfortunately, the worst case is pretty bad. So this is also a benchmark that Red Hat provided, and the way it works goes back to the load balancers that I mentioned briefly before. So from a cold start, if we have a number of huge load balancers and then we delete each of them, what we see is that the C version of it takes, in at least one test set that I had, about 1 minute and 20 seconds and uses 4 gigs RAM. But the ddlog version uses 3 minutes of wall time and over 3 minutes of CPU time, for that matter, and uses a few times as much RAM. And this is a particularly nasty case because each of these load balancer changes, a ddlog sort of ends up processing it twice, once to remove the old version and once to add the new version. ddlog also can't as easily parallelize. This example doesn't show that very well because you can see that the wall time and the CPU time in each case is about the same, but it's true in other cases that northd is much better at handling things in parallel. And then finally, the RAM is explained by the way that ddlog uses indexes so that it's able to support the incrementality, and that just works against it in a case like this. DDLog has a few other issues. It's a new language, so your programmers have to learn it. You have to link it against your other code and make it work nicely. It's going to have bugs in the implementation, and you're going to have to chase those down. And then you're going to have to learn how to deal with the tools. It's a new language paradigm that it's not just the difference between, say, Java and C. You have to learn how to write something in what is, to a lot of people, a pretty esoteric language paradigm. And at least until you finally adopt it, it causes double work for programmers. You have to implement it in DDLog, you have to implement it in C. And for these reasons, and in addition, the fact that DDLog compiles relatively slowly, especially from the viewpoint of C programmers, it's a bit of a problem. And all this adds up to some of the reasons why DDLog does not seem to be the way that OVN is going. Thank you for listening to my talk. I realize that I kind of breezed through this, and I hope that people have some good questions. I'm here for that.